Right. So what is the idea behind the, the strong induction? So let's see, what is the similarity? I think it's a good idea to compare the similarities. Okay? Similarity is what? You're proving the base case in both the cases. It is in induction step, sorry, induction hypothesis. You're assuming a lot more, and that's why it's called strong induction. You're basically asking for a lot more stronger condition. So what is that? So again, you say basically the base case P naught is true, P of n naught, right? This is the base case. Then you show that P1 and P2 and dot 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 Pn implies Pn plus 1 is true for all positive integer. And this is what leads to what? A strong induction. Whereas remember, for the other one, you had what? P1 is true, right? Or P of n naught is true. And then you are showing that P of k or P of n implies P of n plus 1, right? Here, when you're saying and, that means you're assuming this to be true, this to be true, this to be, implies that Pn plus 1. Is that okay? So here our assumption in our assumption, what we'll have is in our induction hypothesis, we'll have that we'll assume for everything less than that to be true. Make sense? Okay, so let's write down a nice solution to this. So use strong induction to prove that any integer n greater than 2 can be written as product of y n greater than 2, n greater than 2. Okay, so base case is what? So Pn. By product of prime, we mean basically it can be by itself as well. Okay, because you know 5 is also there, right? 5 is 5 times 1. So Pn is that what? N is product of okay. So now base case. Base case is what? P of 2 is true. Why is that true? Because 2 can be written as 2 to the power 1. Yeah. So it can be written as a product of primes. Yeah. Does that make sense for the base case? Yeah. So step 1. Now, what is different is in step 2, you're assuming induction hypothesis that Pk, or we can say, well, let's start using n. Huh? So Pn or Pk is true for all n or all k less than equal to. Do you see the difference here? That you are not just assuming Pk is true. You're assuming Pk is true for all k less than equal to what? M. Yeah. Now we need to prove for what? Step 3, prove for n plus 1. Yeah. There should not be a confusion. Oh, sometimes you're using k, sometimes you're using k plus 1. Here, because I want to enumerate all of them, so I'm saying Pk is true for all k. If you don't like that, you can say, if you don't like that, so suppose you say, no, I don't like that, that's fine. Assume Pi is true for all I, just to keep consistency, from all I from what? 2 to k. Okay. Now step is to prove for then k plus 1. Is that okay? Make sense? Now k plus 1. Now there are two cases. K plus 1 is prime. Say P. So case 1. K plus 1 is prime, say P. Then k plus 1 equals to P. So that is k plus 1 is written as what? As product of primes. right? Yeah, in that case, if k plus 1 is already prime, then it's already written as product of primes. We are done. Yeah. Case 2, we don't know about k plus 1. It could be prime or it could be composite, right? So if it is not prime, then the next case is what? Case 2. K plus 1 is not prime. Yeah. This means what? What is the definition of not prime? This implies there exists, say, P a prime. Yeah. And this prime is greater than or equal to 2. There exists, let's just write it down neatly. There exists prime pre greater than or equal to 2 such that what? P divides k plus 1. Right? That's what the composite is, right? If it's not prime, there is a prime divisor. Yeah, we don't care about the size of this prime divisor, but all we know is that it is going to be that it divides basically k plus 1, right? And it's greater than or equal to 2 because it's a prime. Yeah. So that means what? Therefore, I have k plus 1 equals to p times some d, where d is what can we say about d? D is less than k plus 1 and greater than or equal to 2. Right? Why? Again, let's say why. Why is that the case? Because if d is equal to, or d can be 2, right? But d cannot be 1. If d is 1, then we are saying again that k plus 1 is prime. That is already exhausted in the previous one, right? So if I'm saying d plus 1, so if I'm saying k plus 1 is not prime, that means it can be written as product of a prime times a d, where d is between this guy, right? Okay. Now, but by induction hypothesis, now d lies in the range of the induction hypothesis, right? For that, it is true. Or you can say, if you really want to make it look like this, you can say d is less than k plus 1. That is same as saying d is between that. Yeah. So therefore, by induction hypothesis, d is product of powers of prime, right? So d is, I'm going to write p1 to the power e1, l to the power el for primes p1 to pl and numbers and positive integers and positive integers e1 to el. Yeah, some of them. We don't know what is the number of them. We don't know that what primes they are. That's not our concern at all. Okay. So therefore, what do we get? We get k plus 1 is p times e1 to the power e1, pl to the power el. Therefore, what? Therefore, k plus 1 can be written as the product of this means what? This means pk plus 1 is true. Therefore, by strong induction, Pn is true for all n greater than or equal to